Okay, in section 2.2, we're going to learn how to use models to explore spatial patterns and processes. But before discussing specific models and examples, I would like to introduce some more concepts to prepare you, okay? So the first pair of concepts, they are phenomenological and mechanistic models. Actually, phenomenological models, they are empirical models. I've introduced them before. They care only about the statistical relationships among different variables. They do not care much about the mechanism behind the statistical relationship. On the other hand, we have mechanistic models. They are also known as process models. Okay, let's just use process models. They are easy. This phrase is easier to read. Okay, a hypothesized relationship specified in processes that are thought to have given rise to the data. And the model components have real-world counterparts, but these may not be observable directly. And they're concerned primarily with explaining why. So they are the opposite of empirical models, because empirical models, they do not care about explanation. Okay. And another pair of concepts, prediction and explanation. Okay, they are not the same. Okay, explanatory modeling usually leads to empirical models. Okay, predictive modeling usually leads to process models. And there is this asymmetry between prediction versus explanation. You can predict with a good explanation because, after all, you know the mechanism. From process models, so you know how to explain the specific process behind the phenomenon. With that, you can also predict, right? But you cannot explain with only a good prediction, which means that you could not establish process models based on empirical models, but you can create empirical models based on process models. And here we go. The first example I want to discuss about using models to explore spatial patterns and processes. So this example here is about reciprocal links between pattern and process. It's a model for forest structure, okay? And the content of this paper is this, okay? Firstly, the author argued that rarer species, they are more aggregated than more common ones, which means that rarer species, they like to get together to form clusters, to live together, okay? And since rarer species, they are more aggregated than more common ones, then population of a species is negatively correlated with the strength of its spatial aggregation. So population of a species is a measurement of rarity. If the population is pretty small, it means that the species is rare, right? So population of a species is negatively correlated with the strength of its spatial aggregation. If that is the fact, is it possible to address species demography from spatial pattern? So at the very beginning, the argument is that, okay, the rarer a species is, the more that species is spatially aggregated. The question is, if we find a spatial pattern, for example, a species is very aggregated within the space, can we estimate the population of that species? Because population and the strength of the spatial aggregation, they are what? They are negatively correlated, right? So in order to verify or to demonstrate or to answer this question, say that The authors of this paper, they created a model based on this argument. Population of a species is negatively correlated with the strength of its spatial aggregation. So model description for this simple representation of forest structure. Initiation, individuals of a single species located at random. Of course, each individual can be considered as a tree, a grass, or an animal. But anyway, it's individuals in a forest, right? Each model time step, and each time step is a generation. We randomly select n pairs of individuals. The first member dies. The second member reproduces by adding a new individual to the population at a random distance and direction. Okay, and how to decide the distance? Distance drawn from a negative exponential distribution. So here we're not going to dig deep about the exponential distribution, but you only need to know that distance is randomly drawn from a pool. Okay, this pool is exponential distribution. So for each step, we do these several things. So these are rules for this model. Okay, I will repeat it again. Randomly select n pairs of individuals, and the first member dies. The first member of each pair dies. The second member of each pair reproduces by adding a new individual to the population at a random distance and direction. Okay, then these authors of this paper, they defined something called neighborhood density function, NDF, to quantify the aggregation, spatial aggregation. Okay, NDF or omega quantifies the average pattern that an individual tree might experience in its neighborhood. So how to quantify? If eventually you have an NDF of this species equals 1.0, then we see that the spatial pattern is random. There is no aggregation. If NDF is larger than 1.0, we say there is aggregation. The larger, the stronger. The larger the NDF, the stronger the aggregation. If NDF, on the other hand, is smaller than 1.0, there is no aggregation. Instead, there is segregation. Okay, so we were talking about the negative correlation between population and the spatial aggregation. Population itself has been quantified. Population is a value, is a number, should be an integer, right? So how about the quantification of spatial aggregation? Here we go. We have it in this paper, NDF. Okay, NDF, different NDF values, they are representing different types of spatial pattern, random, aggregation, or segregation. Okay, here comes the output of this paper. So the relationship between aggregation, omega or NDF, right, and abundance N. You can consider abundance as population. Okay, here is the scatter plot. The horizontal axis is for abundance, 0, 200 until 1000, and the vertical axis is for the log 10 NDF. It's a log value to rescale this axis to make it represents a larger value, easier to represent larger value, but you can consider this simply as NDF. Okay, so yeah, so this scatter plot is based on 200 model simulations, which means that that model has been run for 200 times, each one lasting 200 generations. So we have 200 black dots here. Each one represents the result of a model running after 200 generations. What are those results? The eventual, the final abundance of the simulation, and also the NDF after 200 times of what? of model running, or 200 generations. Okay, so what's the relationship here? The higher the abundance, the lower the NDF. It's very straightforward, right? This scatter plot tells you that that argument is correct. What argument? There is negative correlation between abundance or population and spatial aggregation. If the population is high, then the aggregation is weak because all those black dots, they have lower NDF value. If the population is small, which means that some black dots on the left side of the scatter plots, if they are the case, it means that this species is very rare. Okay, and if the species is very rare, they have higher NDF, right? Okay, then the authors, they compared different simulations with different n value abundance. So on the left side, we have 1, 2, 3, three figures, two spatial patterns, and one scatter plot. And on the right side, we have another group of figures showing the same thing. The difference is that for the left side, the population is only 200. On the right side, the population is what? Is 800. So initially, at the very beginning, you can say that the n value is equal to 200 and the NDF is more than 1.0. There is already aggregation. On the right side, n value is 800. If you compare these two species, obviously the left one is rarer, right? And on the right side, the less rare species has a spatial aggregation NDF value of 0.999, very close to 1, but we should say there is segregation. So at the very beginning, we can already say that the less the population, the stronger the aggregation, right? The more population of the species, the weaker the aggregation. After 200 generations, this phenomenon is more obvious, right? So the NDF value for the rarer species is 1.8, pretty strong spatial aggregation. And you can see it from this figure, right? There are small clusters and there are empty species. There is empty space within this area. It's very obvious aggregation. On the right side, there is also aggregation because the NDF value is larger than 1.0, but much weaker than the rarer species, right? So again, these four figures, they have verified the argument again. There is negative correlation between population and spatial aggregation. Okay, over time, the virtual forest, of course, it's a virtual one because this forest only exists in your simulations, becomes more aggregated than its initial random pattern, right? After 200 generations, if you compare each species to its initial state, the aggregation becomes stronger, right? And here we have two curves showing you the change of NDF by generations. On the left side, we can say the variation of NDF is very strong from 1.0 to 3.0 for this rare species. On the right side, it's similar. There is also variation of NDF, but compared to the left one, it's relatively stable, and the absolute value here is also small, right? Because this curve is vibrating around 1.0, but on the left side, you can say most of the values for values of NDF for this rare species, they are larger than 2.0. If you draw a horizontal line here, you will see that. Okay, okay. So this is a discussion of the paper using a very simple model to explore the spatial patterns of different species in a forest. It's very simple and straightforward. Okay, here there is a net logo model for this for the model proposed by this paper, and you can find this model from Carmen. Okay, there is a zip file in Carmen called netlogo base models. You need to download it using WinRAR or other um, unzip software or decompression software to unzip it, and you should have a folder like this. I'm going to show you a folder like this, netlogo base models. Okay, and also I would like to show you how to use it. You go to netlogo, the newest version. I'm not sure if I'm having the newest, but 3.0.4 is good enough. You go inside, file, open, find the folder, unzipped folder of netlogo base models, and open it. And you go to base models, and here is 2.2, right? So 2.2. This is the model I put in the slide. And one thing I want to talk about these models you're going to encounter in slides. You're going to see a lot of models in the rest of the semester. They are in the slides, but I don't necessarily have enough time to demonstrate all of them, especially this is an online video. So what I did is giving you all those parameters, as many as possible, and their meanings here, and also their name and possible outcome or output. Okay, and you should go there, find this nlogo file like I did, and play with it a little bit. I'm not saying that you should memorize the functions of every component here, but you should know how this model runs. And if you are pretty interested in it, I would suggest go to the code tab to read the codes. Okay, and also there is more information in info tab about this model if you want to cite it in your paper, how to do that, copyright and license. And if you want to know more, you can go back to your textbook, and you should be able to find it in section 2.2, for example, for this specific model. Okay, okay, let's continue. I will just let you play with it. It's a pretty simple model. And the next a pair of concepts I want to introduce before going further is first and second order structure. They are used to represent two different types of spatial patterns. First order is for global patterns. Second order structure is for local or neighborhood patterns, okay, spatial patterns. Why do we need them? They help identify the generating processes. If there is a first order structure identified within a specific area, there must be some kind of global processes happen here to make this first order structure happen. Similarly, if we have found out there is second order spatial pattern here, then there must be some kind of local processes before this pattern to make this pattern happen. Okay, so a spatial pattern can be very complex. First order and second order structures, you can also consider them as null models. Okay, an actual spatial pattern can have one component, okay, which means that it could be first order or second order, or there could be both of them in one pattern, first order and second order, or there is a very special situation that there is no first order, neither second order. Okay, so spatial pattern can be more complex than simply first or second order. Okay, so what are they? First order structure. Here is an example. Here is an example for the spatial pattern of first order structure. Intensity of event. Each dot can be considered as an event. Intensity of event across space varies following a function of some underlying covariate, which means that, okay, let me finish the definition first. And the generating process, the process who generated this pattern, this first order structure, involves something that varies across space with no interaction between events. Pretty important, I will repeat, with no interaction between events. Okay, what does it mean? It means that the first sentence means that how did these dots happen? I mean, who decided the locations of these dots? Locations of these dots, they were decided by a function. This function can be a quantified mathematical function or can be simply a phenomenon. Okay, that function or that specific phenomenon, they decided how these dots distribute. Okay. And the second sentence here means that all these dots, they do not affect each other's location. Their locations are only decided by that function or by that process or by that phenomenon. Okay, they are independent from each other. One dot's location does not affect any other dot's location within this space. This is first order structure. Sometimes it is also called non-stationary or inhomogeneous spatial patterns. Okay, that's first order structure. Second order structure, this is an example. If you compare with the first one, obviously there are clusters here, right? Second order structure means there is spatial dependence. The process who generated this structure involves local influence of the events themselves. And location of events is influenced by other events. So this is the opposite situation of first order structure, because here there is no so-called phenomenon or function manipulating all these dots. Instead, a dot's location is affected by other dots. Okay, in first order, that is something does not exist. All those dots, their locations are independent from each other, but here it involves local influence of the events themselves, which means that, okay, let's just define a local area like this, okay, generally like this. Within this neighborhood or within this local range, all those dots, they affect each other in terms of locations. Okay, location of events is influenced by other events. Okay, for example, this dot's location is affected maybe by this one, by that one, but maybe not by that further one. But it's possible it is also affected by the further one. It depends on the specific situation, the context. But here you should know there is spatial dependence. Locations of dots are affected by other dots. Okay. Seed dispersal, the model I mentioned before, right? To represent what? To represent the structure of the forest. Okay, that spatial pattern, that aggregation created by different species, that pattern was second order. Okay, I will stop here for this video and I will see you in the next video. Thank you.